Welcome to Tanks 101. Hello, I'm Philip Myers, Director of PEMY Consulting. In 2012, over 130 billion gallons of gasoline was used in the United States alone. Most of it was hydrocarbons. In this screencast, we talk about some fundamental ideas related to hydrocarbons and its chemistry. Why hydrocarbons, you ask? Well, if you deal with a hydrocarbon and are going to own it, store it, handle it, work with it, in a hydrocarbon plant, regulate it, leak it, spill it, emit it, or do anything with it, it pays to have a little bit of knowledge about it. This little bit of knowledge can help you do your job better and even keep you and your colleagues safe at work. As you might expect, the word hydrocarbon has something to do with the two elements, hydrogen and carbon. In fact, a hydrocarbon is just that, a molecule made up of hydrogen and carbon atoms only. There are many other organic compounds that are comprised of carbon, hydrogen, and other atoms, such as oxygen, nitrogen, or sulfur. For example, alcohols have hydrogen, carbon, and oxygen in their molecular structure. Hydrocarbons can be gases, liquids, or solids. It is the hydrocarbons that make the petroleum world go round. You use hydrocarbons every day for heating, operating vehicles, traveling, clothing, plastics, medicine, and many other products. In this slide and the next, we will talk about the periodic table and its relationship to elements. A molecule is formed when two or more atoms join together chemically, meaning that a chemical bond between atoms has been formed. A compound is a molecule that contains at least two different elements. An example is nitrogen gas, where two nitrogen atoms bond to each other to form a nitrogen molecule. This molecule is not a compound because it only has one type of atom, nitrogen. But water is, as we all know, H2O, and has two hydrogen atoms bonded to one oxygen atom, and is therefore a compound. Hydrocarbons are compounds that contain only hydrogen and carbon atoms. Later, we will show some examples of how hydrocarbons can be represented. We will not be able to cover very many compounds, but we will cover three important classes of hydrocarbons: alkanes, alkenes, and alkynes. You're already familiar with one alkane, and that is octane, which is a major component of gasoline. Finally, we will discuss the basic combustion properties of hydrocarbons, which is important to understand for at least two reasons. It is the combustion of hydrocarbons that powers vehicles, furnaces, boilers, and countless other kinds of equipment. Another reason is, of course, safety. The more you know about the properties of hydrocarbons, the better you will be able to understand the safety issues associated with handling them. When I was a first grader, we had to memorize the quote shown below the periodic table, and we recited it in our science class. It fascinated me that everything in our bodies is made up of atoms which combine to form molecules, and which are the building blocks of everything in the universe around us. We won't go into details, but it is useful to know that all known atoms are compressed into this one pager. There are about 90 stable elements that make up everything in our world and the universe. Hydrogen, which is an ingredient of hydrocarbons, is circled at the top left and is the lightest element. As shown by the inset, it has an atomic number of 1 above the symbol H for hydrogen. This means that there is 1 proton in the nucleus. Now look at the other circled element, which is carbon. It has an atomic number of 6, meaning that it has 6 protons in the nucleus. As you move from left to right or from up to down in the periodic table, the atomic number or number of protons increases. The atoms are arranged in columns which have similar properties. For example, all the elements in the first column have an extra electron for the purpose of combining with other elements. And this first column has many similar properties. Note that the atomic mass of carbon is about 12, shown below the symbol, which means that for a fixed quantity of atoms, the weight of carbon will be about 12 times greater than that of hydrogen. Because of the number of electrons in the reactive outer portion of the elements, compounds combine in fixed proportions. For example, water is H2O, so two hydrogen atoms combine with one oxygen atom. Note that even though hydrogen and oxygen are both gases, the end product is water. Nothing at all like the gases hydrogen and oxygen, as we know from observing a lake or the ocean. The simplest hydrocarbon is methane, a colorless, odorless, and flammable hydrocarbon gas. Hydrogen has one electron for sharing with another element, but carbon has a valence of 4, meaning that it can share 4 electrons with other elements. Methane has 4 hydrogen atoms bonded to one carbon atom. Methane comprises the bulk of natural gas used in your furnaces and kitchens. If you ever listen to a conversation in the engineering department of a refinery, don't be surprised if you hear them tossing around phrases like C4, C5, C6, C8. They are referring to the number of carbon atoms of a particular molecule of interest in the processing scheme they are discussing. This will become clear as we move forward. The word organic is often meant to mean contains carbon. When you take organic chemistry in college, you are studying the chemistry of carbon and consequently the chemistry of life. If other elements such as oxygen, nitrogen, or others are combined with hydrocarbons on an atomic basis, then the stuff of life can be created. There are over 4 million organic compounds known, and about 100,000 new compounds are discovered annually. When you hear a word that ends in "ene," as in ethylene or ethene, for a hydrocarbon, that usually means that it has a double bond. A double bond means that 2 of the 4 carbon bonds combine with themselves and not with other elements. Likewise, hearing an "ine," as in ethyne, means that the carbon atom has a triple bond. This, of course, means that 3 of the 4 carbon bonds are combined with themselves and not with other elements. We'll talk about this more later, but the photo shows some interesting factoids. Ethene gas is a common hydrocarbon. It's colorless and odorless. Double bonds in hydrocarbons make them generally more chemically reactive than their single bonded cousins. A double bond in a hydrocarbon, for example, can be used to green bananas and ripen them quickly on contact with a reactive gas so that producers can pick and ship green bananas all over the world without worrying about them spoiling before they hit the supermarkets. Triple bonded carbon atoms are in acetylene, whose proper actual chemical name is ethyne. You'll note that for the simpler hydrocarbons that have been used for a long time, there's often 2 or more names. One of the names, such as ethylene, has been named way back before the formal nomenclature was created for hydrocarbons. Acetylene, used in oxyacetylene cutting torches, was named long before chemists came up with a formal nomenclature. The formal name of acetylene is ethyne. Unfortunately, we won't be able to talk about all the different naming conventions for organic compounds. Because of the complexity of the atomic structure for organic compounds, various means of representing them have evolved. This table has 5 columns, each of which is a different representation of the same compound. The simplest organic molecule is written CH4, where the subscript 4 indicates that there are 4 hydrogens attached to one carbon. The third column shows a more pictorial representation, explicitly showing the hydrogen atoms and the atomic bonds attached to the carbon atom. The ball and stick model accounts for the tetrahedral shape of the molecule. It is a 3-dimensional representation, as is the next column, called the space-filling model. For simple compounds, it's sufficient to write the formula as shown by the second column, or just refer to it by name. But when the size of the compound is large, scientists often use a more pictorial representation to understand and explain the properties of the compound more effectively. The first major group of hydrocarbons that we'll talk about are the alkanes. For example, ethane, propane, butane, pentane are all alkanes, or as are heavier alkanes such as octane used in gasoline. The general formula is CnH2n plus 2. For example, octane would be C8H2 times 8 plus 2 would be C8H18. They all undergo similar chemical reactions. They're also called saturated. This means that they don't have any double bonds. Alkanes are obtained from crude oil distillation processes in refineries. They're mainly used as fuels, and the number of carbons in an alkane can be quite large, but there's not a lot of demand for them because they don't burn. The largest typical alkanes that are used are waxes. Here we show how carbon can form atomic bonds and configure itself in different ways. In A, we have two straight-chain hydrocarbons, ethane and propane. One has 2 carbons and the other has 3 carbons. They are connected to each other with single bonds. In B, we see that the same 4 carbon atoms can combine in 2 different ways by forming a branch instead of a straight chain. This is possible because 4 carbon bonds can be arranged in any order. In C, there's a double bond. 2 of the 4 carbon bonds combine with each other instead of combining with other elements. Finally, in D, we see that cyclical compounds can be formed from a carbon atom. Cyclohexane is a saturated ring, meaning that there are no double bonds. The benzene molecule has a specialized set of double bonds that resonates within the atomic structure. The next major group of hydrocarbons is the alkenes. They fit the formula CnH2n. This formula has 2 less hydrogens in a molecule than does the equivalent alkane. The reason for this is that the double bond that's in the alkene uses up 2 of the 4 hydrocarbon bonds. Alkenes are referred to as unsaturated hydrocarbons because of the double bond. Another name for unsaturated hydrocarbons is olefins. They are much more reactive than alkanes, and you can think of the double bond as an unstable atomic bond. The importance of these compounds is in making polymers and plastics, hydrogenation of vegetable oils to make margarine, and the hydration of ethene in refineries to make ethanol. Here we come to the third important hydrocarbon group called the alkynes. The one you are most familiar with is acetylene. While the name ends in "ene," as if it were an alkene, it is not. It's an alkyne. This is because of the historical hangover in organic compound naming conventions and because of tradition. The common name remains acetylene. However, its correct chemical name is ethyne as shown. In any case, it is so highly reactive and unstable that it must be absorbed into acetone, another organic compound with hydrogen, carbon, and oxygen, so that it does not decompose or detonate. Cylinders of acetylene in acetone are widely used for oxyacetylene cutting torches. The alkynes are the least common of the 3 groups of hydrocarbons we have discussed. We now talk about hydrocarbon combustion. The word exothermic means that a chemical reaction, which is in this case combustion, gives off heat. While the formula shows 2 simple end products, in reality there are many complex organic compounds formed during combustion. However, since the bulk of the combustion products are mostly carbon dioxide and water, the process can be idealized by the simple formulas given here. CH4 plus 2O2 for oxygen yields carbon dioxide plus water. Although we're focusing on hydrocarbons, it's important to understand that they are only a small subset of the millions of organic compounds that exist. The table shows that by simply substituting a hydroxyl group, that is, an OH, oxygen and hydrogen group, for a hydrogen atom in the original hydrocarbon results in an alcohol. Alcohols are a totally different compound than the hydrocarbons and have unique properties all their own. Organic chemistry is a vast and complex subject. We've only scratched the surface. However, it's important to understand the basic terminology used by everyone in the hydrocarbon business. For more information, check out PEMYconsulting.com. Thank you.